Paul Dirac was born on August 8, 1902, in Bristol, England, into one of the most dysfunctional families in the history of science. His father, Charles Dirac, was a French-Swiss immigrant who taught French at a local technical school. Charles was a tyrant, a man who ruled his household with rigid discipline and an obsession with control. The family home was divided. Charles insisted that French be spoken in the dining room where he ate with young Paul, while Paul's mother and siblings spoke English in the kitchen. If Paul made a grammatical error in French, he was punished. If he spoke at all without being spoken to, he was silenced. The message was clear. Speech was dangerous, silence was safe. Paul learned to say nothing unless he had something precise to say. He learned that words should be chosen with mathematical exactness, that every statement should be carefully considered before being uttered. This wasn't just a personality quirk, it was a survival mechanism, a way to avoid his father's wrath. The result was a boy, and later a man, of almost pathological reticence. Dirac became famous in the physics community for his silence, for his economy with words, for his refusal to engage in small talk or unnecessary conversation. Colleagues joked about Dirac units of speech, 1 word per hour. But behind this silence was a childhood of fear and emotional deprivation. His family life was tragic in other ways too. Paul had an older brother, Reginald, who was also subjected to their father's harsh regime. But while Paul retreated into silence and mathematics, Reginald couldn't cope. In 1924, when Paul was 22 and beginning his studies at Cambridge, Reginald committed suicide. The family was shattered, though Charles seemed incapable of understanding his role in the tragedy. Paul never spoke much about his brother's death, but it haunted him. Years later, he would say that the happiest time of his life was when his father died, finally freeing him from that oppressive presence. But if Paul's emotional life was stunted, his intellectual life flourished. He was brilliant at mathematics from an early age, able to manipulate symbols and equations with extraordinary facility. He attended the Merchant Venturers Technical College in Bristol, where his father taught, studying electrical engineering. It was a practical education, not the classical physics and mathematics of Cambridge or Oxford, but applied mathematics, engineering problems, circuit theory. This engineering background would profoundly influence his later physics. While other theoretical physicists thought in terms of physical pictures and analogies, Dirac thought in pure mathematics. Equations were reality for him. Pictures were unnecessary complications. In 1921, Dirac graduated with a degree in electrical engineering, but there were no engineering jobs available in post-war Britain. He stayed in Bristol, taking courses in mathematics, essentially giving himself the theoretical education he'd missed. Then, in 1923, he won a grant to study at Cambridge, the center of British physics. He was 21 years old, painfully shy, socially awkward, and about to enter the most exciting period in the history of physics. Quantum mechanics was being born, and Dirac would become one of its principal architects. When Dirac arrived at Cambridge in 1923, physics was in crisis. The old quantum theory, Bohr's model of the atom with its ad hoc quantization rules, worked for simple cases but failed for more complex atoms. Something was fundamentally wrong, but no one knew what. Then, in 1925, everything changed. Werner Heisenberg, working in developed matrix mechanics, a new mathematical framework for quantum phenomena based on non-commuting matrices. Heisenberg's paper was revolutionary but almost incomprehensible. Even physicists struggled with it. Dirac's supervisor at Cambridge, Ralph Fowler, received a proof copy of Heisenberg's paper and gave it to Dirac to read. Dirac looked at it, found it confusing, and set it aside. But a week later, something clicked. He realized that Heisenberg's non-commuting matrices were related to something he'd seen before, Poisson brackets from classical mechanics. There was a deep analogy, a mathematical structure connecting classical and quantum physics. Dirac began working feverishly, developing his own formulation of quantum mechanics, one that was more general and more elegant than Heisenberg's. Where Heisenberg had discovered quantum mechanics by focusing on observable quantities, Dirac was discovering it through pure mathematical reasoning, by finding the right mathematical structure. Within months, working largely in isolation at Cambridge, Dirac had developed what would become the transformation theory of quantum mechanics. He introduced the concept of quantum states as vectors in an abstract space, operators acting on these states, and eigenvalues corresponding to observable quantities. His notation, the bracket notation with symbols like psi for quantum states, became standard throughout quantum physics. It was a triumph of mathematical abstraction. Dirac wasn't thinking about physical pictures of atoms or electrons. He was thinking about mathematical structures, symmetries, transformations, and this abstract approach was incredibly powerful. In 1926, Erwin Schrödinger published his wave equation, providing yet another formulation of quantum mechanics, one based on familiar wave equations and partial differential equations. Now there were three formulations: Heisenberg's matrix mechanics, Schrödinger's wave mechanics, and Dirac's transformation theory. Were they all describing the same physics? Schrödinger proved that his and Heisenberg's approaches were mathematically equivalent. Dirac went further, showing that all three were special cases of a more general framework. He had found the common mathematical structure underlying all of quantum mechanics. By 1927, still only 25 years old, Dirac was recognized as one of the leading theorists in quantum mechanics, alongside Heisenberg, Schrödinger, and Bohr. But he was also the strangest of them, completely focused on mathematics, indifferent to physical intuition, silent in discussions, socially isolated. His colleagues respected his brilliance but found him impossible to talk to. There's a famous story from the 1927 Solvay conference, where all the founders of quantum mechanics gathered. During a discussion, someone made a comment and looked at Dirac for a response. After a long silence, Dirac said, "That is not a question, it is a statement," and said nothing more. This was Dirac, precise to the point of absurdity, unable or unwilling to engage in normal human conversation. But Dirac's greatest achievement was still to come. In 1928, he tackled a problem that had been bothering physicists: how to make quantum mechanics consistent with Einstein's special relativity. Schrödinger's wave equation worked beautifully for describing electrons in atoms, but it wasn't relativistic. It didn't properly account for effects at high velocities. Several physicists, including Schrödinger himself, had tried to write a relativistic wave equation, but these attempts led to problems: negative probabilities, negative energies, results that made no physical sense. Dirac approached the problem with his characteristic mathematical focus. He was looking for an equation that was both quantum mechanical and relativistically invariant, an equation that would reduce to Schrödinger's in the non-relativistic limit, but would work correctly at all speeds. The obvious approach was to use the relativistic energy-momentum relation E2 equals P2C2 plus M2C4, but taking the square root led to mathematical complications. So Dirac tried something audacious. He looked for a linear equation, an equation where energy and momentum appeared to the first power, not squared. This required introducing new mathematical objects, matrices now called Dirac matrices or gamma matrices, with special properties. When Dirac worked out the mathematics, something miraculous happened. The equation he derived, now called the Dirac equation, not only correctly described relativistic electrons, but it automatically predicted electron spin. Spin had been discovered experimentally a few years earlier. Electrons behaved as if they were spinning, possessing angular momentum even in their ground state. But no one understood where this spin came from. It had to be added to quantum mechanics by hand. Dirac's equation predicted it automatically, as a consequence of combining quantum mechanics with relativity. It was an almost magical result, like deriving the existence of color from Maxwell's equations. But the Dirac equation had a disturbing feature. It predicted not just positive energy solutions, normal electrons, but also negative energy solutions. What did these mean? At first, Dirac thought they might be artifacts, unphysical solutions that could be ignored, but they wouldn't go away. The negative energy states were as mathematically necessary as the positive ones. So Dirac made a bold proposal. The negative energy states were real, but in the ordinary vacuum, they were all filled, an infinite sea of negative energy electrons. Because of the Pauli exclusion principle, which says two electrons can't occupy the same state, positive energy electrons couldn't fall into these filled negative states. The vacuum was stable. Then Dirac made an even bolder prediction. If you gave a negative energy electron enough energy, you could promote it to a positive energy state, leaving behind a hole in the negative energy sea. This hole would behave like a particle with positive energy and positive charge, the opposite of an electron. Dirac initially thought this might be a proton, but that didn't work mathematically. So he predicted something no one had ever seen: an antielectron, a particle identical to the electron in every way except with opposite charge. It was a stunning prediction: antimatter, arising purely from the mathematics of relativistic quantum mechanics. In 1932, just 4 years after Dirac's prediction, Carl Anderson discovered the positron in cosmic ray photographs, the antielectron Dirac had predicted. It was one of the great triumphs of theoretical physics, a purely mathematical prediction confirmed by experiment. Suddenly, Dirac's equation was recognized not just as a correct description of electrons, but as a window into a deeper structure of reality. In 1933, Dirac and Schrödinger shared the Nobel Prize in Physics for their contributions to quantum mechanics. Dirac was 31 years old, one of the youngest physicists ever to receive the prize. Dirac's success with the relativistic electron equation solidified his philosophy of physics, a philosophy he would hold for the rest of his life. Mathematical beauty is a guide to truth. For Dirac, the most beautiful equations were likely to be correct, even if they made strange predictions, even if they contradicted physical intuition. The Dirac equation was beautiful, elegant, symmetric, inevitable, and it was right. This became Dirac's creed. It is more important to have beauty in one's equations than to have them fit experiment. This sounds arrogant, almost mystical, but for Dirac, it was a practical guide. Beautiful theories might disagree with experiment initially, but experiments could be wrong or incomplete. Beautiful theories endured. This philosophy led him in interesting directions. In the 1930s, Dirac became interested in the large number coincidences in physics. The fact that certain dimensionless ratios, like the ratio of electromagnetic to gravitational forces, are enormous numbers around 10 to the 40. He speculated that these weren't coincidences, but hints of a deeper structure. This led him to propose that fundamental constants like the gravitational constant might vary with time, a radical idea that most physicists rejected. Dirac pursued it anyway because he found it beautiful and intellectually compelling, even though experimental evidence didn't support it. He also became increasingly critical of the direction quantum field theory was taking in the 1930s and 1940s. As physicists tried to calculate properties of particles using quantum field theory, they kept encountering infinities, divergent integrals that gave infinite answers. The solution, developed by Richard Feynman, Julian Schwinger, and Shinichiro Tominaga, was renormalization, a mathematical procedure for subtracting infinities in a systematic way. It worked brilliantly. Quantum electrodynamics became the most accurately tested theory in physics. But Dirac hated it. He thought renormalization was an ugly mathematical trick, a way of sweeping problems under the rug rather than solving them. "I am very dissatisfied with the situation," he said, "because this so-called good theory does involve neglecting infinities which appear in its equations. No matter how successful the theory is, I feel we cannot consider it as a satisfactory theory." His younger colleagues found this attitude frustrating. Renormalization worked. It made predictions that agreed with experiment to 10 decimal places. What more did Dirac want? But Dirac wanted beauty, elegance, a theory that didn't require mathematical sleight of hand. He spent decades trying to find an alternative approach to quantum field theory, one that would avoid the infinities altogether. He never succeeded, and quantum field theory with renormalization became the foundation of the standard model of particle physics. But Dirac never accepted it. He remained convinced that a more beautiful theory was waiting to be discovered. This stubbornness might seem misguided, but it was of a piece with his earlier triumph. The Dirac equation had seemed wrong initially. Those negative energy states appeared to be a mathematical flaw. But by taking the mathematics seriously, by believing in the beauty of the equation, Dirac had discovered antimatter. Perhaps his instincts about renormalization were also correct, and a more beautiful theory does await discovery. Or perhaps this was a case where beauty misled him, where the ugly duckling of renormalization was actually the correct approach. Either way, it shows the double-edged nature of Dirac's philosophy. It had led him to greatness, but it also left him increasingly isolated from mainstream physics in his later years. Dirac's personal life was as unusual as his physics. In 1937, at age 34, he married Margit Wigner, the sister of the physicist Eugene Wigner. This was surprising to everyone who knew Dirac. He seemed so completely devoted to physics, so uninterested in human relationships, that marriage seemed out of character. But Margit was persistent, warm, and willing to navigate Dirac's peculiarities. She had 2 children from a previous marriage, and she and Paul would have 2 more daughters together. By all accounts, Dirac was a devoted father, patient and gentle with children in a way he never was with adults. Perhaps children's directness appealed to him. They didn't require the complex social navigation that adult conversation demanded. Stories about Dirac's literal-mindedness and social awkwardness are legendary in physics. Once, after giving a lecture, someone said, "Professor Dirac, I don't understand how you derived the equation in the 3rd line." Dirac said nothing, just stood there silently. After an uncomfortable minute, the questioner said, "Well, aren't you going to answer?" Dirac replied, "That was not a question. It was a statement." Another time, when asked if he wanted tea or coffee, Dirac replied, "Yes." When pressed, "Which one?" He said, "You did not ask which. You asked if I wanted tea or coffee." This wasn't rudeness, it was radical precision. Dirac lived in a world of exact meanings, where words had definitions and statements had logical structure. He was also famous for his economical use of words. Richard Feynman tells a story of sitting next to Dirac at a dinner. After a long silence, Feynman tried to make conversation. "It must be wonderful to be the discoverer of that equation." Dirac paused, then said, "That is not a question." Another long silence. Finally, Dirac volunteered, "Are you working on an interesting problem?" Feynman described his research. When he finished, Dirac said, "That is probably not interesting," and returned to silence. Not malicious, just honest in a way that normal social conventions don't allow. Modern historians and psychologists have speculated that Dirac may have been on the autism spectrum, probably what would now be called Asperger's syndrome. His literal interpretation of language, his difficulty with social cues, his obsessive focus on mathematics, his need for routine and precision, all are consistent with this diagnosis. But in his time, such concepts didn't exist. Dirac was simply seen as eccentric, the strange man of physics. His colleagues worked around his peculiarities because his brilliance was undeniable, and Dirac seemed content with his isolation. He didn't need friends or conversation. He had physics, mathematics, and eventually, his family. In 1932, Dirac was appointed Lucasian Professor of Mathematics at Cambridge, the chair once held by Isaac Newton. It was one of the most prestigious positions in British science, and Dirac held it for 37 years. He was a conscientious teacher, though not an inspiring one. His lectures were precisely organized, clearly presented, but utterly without passion or flourish. He would write equations on the board in silence, explain them minimally, and move on. Students learned from his precision, but were never drawn in by personality or enthusiasm. Dirac couldn't teach that way. It would have required an emotional engagement he didn't possess. In 1969, at age 67, Dirac retired from Cambridge and moved to Florida State University in Tallahassee, where he spent his final years. It was an unusual choice. FSU wasn't a major center for theoretical physics, but the climate was good, the position undemanding, and Dirac seemed to appreciate the distance from the British physics establishment. He continued to work on fundamental problems, still searching for that more beautiful formulation of quantum field theory, still convinced that the infinities of renormalization pointed to a deeper flaw. He also became more reflective about the development of quantum mechanics, giving occasional talks about the history of the field. In these talks, his priorities were clear. He emphasized mathematical beauty, elegant formulations, the search for general principles. He had little patience for phenomenology or experimental details, Those were means to an end, and the end was understanding the mathematical structure of nature. His colleagues sometimes found this attitude cold, but it was authentically Dirac. He had spent his entire life trying to uncover the mathematical laws that governed reality, and he believed he had succeeded, at least for the quantum mechanics of the 1920s. The problems that remained, quantum field theory, quantum gravity, the unification of forces, would require the same approach. Find the beautiful mathematics, and the physics will follow. Paul Dirac died on October 20, 1984, in Tallahassee, at age 82. He was buried in the local cemetery, far from Cambridge and the centers of European physics where he had made his name. In 1995, a memorial plaque was placed in Westminster Abbey, near Newton's grave, honoring Dirac alongside Britain's greatest scientists. The plaque bears the Dirac equation, that beautiful linear formulation of relativistic quantum mechanics that predicted antimatter and changed physics forever. Dirac's legacy is immense and multifaceted. The Dirac equation is one of the cornerstones of modern physics, as fundamental as Maxwell's equations or Einstein's field equations. Every description of electrons, quarks, or other spin particles uses the Dirac equation or its generalizations. The prediction of antimatter was one of the great triumphs of theoretical physics, a purely mathematical prediction, seemingly absurd, that turned out to be correct and opened an entire new domain of physics. Today, antimatter is used in PET scans in hospitals, is studied in particle accelerators around the world, and features in our understanding of the early universe. All from Dirac's insistence on taking his equations seriously. His contributions to the formalism of quantum mechanics are equally important. The Brocket notation, transformation theory, the elegant mathematical structure he developed, these became the standard language of quantum physics. Every quantum mechanics textbook uses Dirac notation, teaches Dirac's formulation. When physicists think about quantum states, operators, and measurements, they are thinking in the framework Dirac created. He took the confusing, ad hoc quantum theory of the mid-1920s and gave it a coherent mathematical structure that has lasted a century. Beyond specific equations and notations, Dirac's philosophy, that mathematical beauty is a guide to truth, has influenced generations of theoretical physicists. This idea isn't universally accepted. Many physicists are suspicious of it, arguing that nature has no obligation to be mathematically elegant, that experiment is the only reliable guide. But the success of Dirac's approach, and the success of other theorists who followed similar instincts, suggests there's something to it. The most fundamental laws of physics do seem to have a mathematical beauty to them. Whether this is because nature is fundamentally mathematical, or because our brains find certain mathematical structures compelling, is an open question. But Dirac's career stands as evidence that aesthetic judgment, properly calibrated, can be a powerful tool in theoretical physics. The strangeness of Dirac the man, his silence, his literal-mindedness, his social isolation, is inseparable from Dirac the physicist. His ability to think in pure mathematical abstractions, to ignore physical intuition, and follow the mathematics wherever it led, may have been connected to his difficulty with human relationships and social cues. While others needed physical pictures and analogies to guide their thinking, Dirac could operate in a realm of pure symbols. This gave him unique insights, but also limited him in some ways. He couldn't communicate his ideas the way Feynman could, couldn't inspire students the way Bohr could, couldn't build research groups the way Heisenberg could. But he could see mathematical structures others missed, and that was enough. In the end, Paul Dirac was exactly what he appeared to be. A man who lived almost entirely in the world of mathematical physics, who found in equations a clarity and beauty absent from human interaction, who believed absolutely that the universe was fundamentally mathematical and that the key to understanding it was finding the right equations. He found some of those equations, the Dirac equation, the transformation theory of quantum mechanics, and in doing so, he changed our understanding of reality. The equations remain, carved now in stone in Westminster Abbey, a testament to the strange, silent man who discovered them and who showed that antimatter wasn't science fiction but mathematical necessity. Dirac's world was one of symbols, symmetries, and elegant equations, and in that world, he achieved a kind of perfection that human relationships and ordinary life never offered him. The most beautiful equation predicted the existence of antimatter. This was Dirac's truth, and it turned out to be true.